So, good evening, everyone. Myself, Pratham Tyagi. And as discussed in the part one stent simulation, we have completed the geometry preparation for the artery balloon and stent assembly overall. After assigning the required material properties described by the customer and establishing the simulation requirement provided by them for evaluating the stent deployment behavior, moving forward, the next step or the important stage is defining the interaction between the components. Since the stent expansion process involves continuous contact between the balloon and stent and arterial wall, accurate interaction definition is critical for obtaining the realistic results. So, under the interaction module of Abaqus, surface to surface contact is created by selecting the relevant surface bodies. In this case, the balloon inside and contact surface are selected as per the deployment requirement. So for contact behavior, the normal contact formulation is defined using the penalty method. For the penalty formulation, we generally define friction because in highly nonlinear contact problems, it helps us achieve the convergence while maintaining the realistic contact pressure between the interacting bodies. For tangential behavior, a friction coefficient of 0.2 is sufficient and is assigned now. Friction plays a critical role during the stent deployment because it controls the sliding resistance between the contacting surfaces. So, without friction, the stent may slide unrealistically during expansion, leading to inaccurate stress and deformation prediction. I hope you are getting my point. A friction coefficient of 0.2 provides a balanced representation of the interaction between the stent system and surrounding the structure. Once the contact interaction are successfully defined, the next step is applying loads and boundary condition. So to ensure that the loading direction accurately represent the physical deployment status, a datum coordinate system is first created. This local coordinate system allows displacement loading to be applied in the desired direction regardless of the global coordinate orientation. So after defining the datum coordinate system in the XYZ directions, we'll assign the proper deployment requirements. The relevant surface bodies are then selected for the load application. The displacement values are applied based on the data provided by the end customer. These displacement control boundary condition for the realistic expansion and in a controlled movement profile rather than a direct force application. After or while applying the boundary condition, only the required degree of freedoms are activated. As we know, if we don't provide the relevant or the realistic condition, we'll end up getting unstable and unrealistic result for this simulation. So after constraining unnecessary degrees of freedom, how it's gonna help? It will ultimately eliminate a rigid body motion and improve solver stability. At the same time, allowing movement in the required direction, it helps us make sure that the model behaves as intended and under realistic deployment condition. So after defining the displacement loading, the next step is amplitude creation. After we apply interaction, after we put up the proper loading condition in the coordinate system, in the required coordinate system, we're gonna be applying the amplitude. As amplitude is extremely important in non-linear simulation, it involves contact and large deformation. So instead of applying the entire displacement instantaneously, the amplitude controls how the displacement evolves throughout the simulation step. There are multiple ways in Abaqus to put up these amplitudes, as in the tabular form, as in the step form, or as in the smooth curve form. So a smooth amplitude curve will be applying, and it helps us allow the load to increase gradually, which improves convergence. Ultimate goal is to get the converged result, because after getting the converged result, we can just do the experimental confirmation of that result. If we don't get the converged result, we gonna be end up getting unstable result or unrealistic result, because more accurately the convergence result are represented, and in this particular process the inflation process of the balloon is represented only after we get the converged result. So sudden loading can introduce artificial stress spikes and numerical instability, which ultimately gonna be affecting the quality of the result. So important best practice while defining amplitude is to include a smooth ramp profiles, avoiding abrupt changes in the displacement, maintaining consistency with the expected inflation sequence, and ensuring that the applied loads or the applied displacement matches the consumer requirement. With the loading condition completed, the model is ready for meshing. As we know, mesh quality directly influences the simulation accuracy, especially in a medical device application where localized stress or the very iterative results are critical. So strains are also critical. The process begins with the seed generation, where the desired element size is specified. A finer mesh is generally preferred in regions experiencing high stress. And in this stent crowns, connectors and contact zone between the stent and artery, coarser mesh may be used in region where deformation gradients are relatively small. After defining the seeds, appropriate mesh are assigned. The mesh generation process is initiated from the selected region to ensure proper element flow throughout the geometry, particularly attentioning into the good aspect ratio, minimizing the element distortion and generating a mesh that can accurately capture the expansion behavior of the stent. Once the mesh is generated, quality checks are performed before proceeding to the analysis stage. After successful mesh verification, the simulation is submitted for the execution. In this project, two separate studies are performed to evaluate different stages of the stent deployment and mechanical response. During the solution process, Abaqus simultaneously considers geometric nonlinearity, contact nonlinearity, and material behavior and frictional interaction. These nonlinear effects are essential for accurately capturing the deployment mechanics of the stent system. Following successful completion of both the studies, the results are evaluated in the visualization module. The primary output reviewed include von Mises stress, equivalent plastic strain, contact pressure, and total displacement. These results ultimately gonna be helping us to evaluate the structural integrity, deployment performance, and overall effectiveness of the stent design before physically prototyping the stent and the balloon assembly. So this is how our software, or our lovely Abaqus software services. So this is how Abaqus serves as a very good tool for medical device deployment, allowing companies like Translumina to validate design virtually, reduce development cost, and ultimately accelerating the product optimization while maintaining high standards for the patient. Beyond the technical benefits, simulations such as these provide significant commercial advantage for multiple customers. So traditionally, validating a stent design would require multiple rounds of physical prototyping, bench testing, and design modification. Each design iteration involves manufacturing cost, testing resources, engineering hours, and project delays. By utilizing Abaqus for virtually validation, many potential design issues can be identified during the development stage or the deployment stage itself. And analysts like us, we can evaluate multiple design variants, deployment strategies, material selection, and loading condition without producing a physical prototype for each scenario. So advanced non-linear solver available in Abaqus allow accurate prediction of stress, strain, contact pressure, and deployment behavior before the actual manufacturing. So as a result, engineering team can make a data-driven design decision earlier in the development stage, reducing network and minimizing the risk of late-stage design failures. So ultimately, simulation-driven engineering enables companies to bring a safer and more optimized product to market, and maintaining high development efficiencies and controlling costs. Thank you so much for visiting both these videos, and I'll be posting more on this channel. For the upcoming video, I'll be posting an RDSO, the train pantograph simulation. So be prepared for that. Thank you so much.